Hello, I'm Sid Roman. For today, I'll be presenting the solution for data scientist coding round. And the first problem is given an ability storing numeric values, design an algorithm to efficiently return all the sum of all the values within a given range L to R. And the follow-up question is how do you approach scale if each tree update must propagate features for downstream ML models? So the logic here will be if a node key is greater than means node key is within the range L and R, include all values, include the its value and search both subtree. So let's say for calculating sum in range 25 to 50, it will start from here and go to both subtree because 40 lies in the range. And if a node key is less than L, it will go to it will prune the left subtree because the left subtree will not include the value. And if a node key and search only the right subtree. And if a node key is greater than or from right subtree and search only left. The time complexity would be O of log n plus k, where n is total nodes and k is nodes in range, and the excess complexity will be O of log n. And also for efficient doing some calculation, I have included subtree sum, subtree minimum, and subtree maximum, and also the node count. Let's say how it will improve the efficiency of the code. So for 25 to 50, the node visited should be this two and to this, and in this side 25 to 50. So this two node is also should also be visited because it is in range 50. But you can see that the nodes are not visited because 45 already includes the sum of its subtree. So the sum will be returned from here to the recursive function, and it will be calculated automatically. So the algorithm doesn't need to visit these two nodes, so it will be more efficient. And for calculating the sum minimum and maximum, and not count all of the calculation is the open time complexity. So it will be more efficient than other approach. And for downstream ML features, we can count mean, range, or normalization, density estimation from this information. And it will be fast because when we insert a new key, all the information like the sum, the subtree sum, the subtree minimum, and the subtree maximum, all will be updated. And for problem two, it says suppose you must restore and retrieve large model load files distributed across a database. Explain how a B-tree supports first search and insert operations at scale. And the follow-up question is how does this apply to feature vector lookups in recommender system? So large model. So let's draw a B-tree. So let's say the B-tree will have three keys and six children. sorry, 4 children. So we can store the information or the large words are stored in the, let's say, in a hard disk space. This is a large words address and it starts from here. So the start address will be stored in one of the keys and it's XYZ. And for the other space information, it will be stored in consecutive trees. So the address will be from this will be sorted in a bit tree manner. So in a bit tree, because we store uh, more than one keys in a level in a node, so the tree depth will be less than a normal binary subtree. So each of the child will have three keys. And for finding a key to the finding a key which is an address to the disk space, what the model nodes are stored. We don't need to clone that much of tree because uh, it will be it will be efficient because more than one key is stored in a node. And for the recommended system, the challenge is the complexity of vector is often too large for n. To find the best vector specific user or item, the system must be retrieved from this. So this is the same thing. So we will be stored, we will store the uh, model OS and for recommender system vector lookups information. The complete set of vector in the disk separately for let's say different users, and it will all be stored with an unique ID in the tree. So when we get the unique ID from the tree, we can fetch the data from the disk space. And the retrieval of unique ID will be efficient because the V tree supports more than one key in a node. Now let's see the problem three. Outline an algorithm for finding a minimum spanning tree in a string distributed system. Follow-up question is, in what real-world ML scenario would you use MST's sensor network feature selection? So, one of the algorithms for finding a minimum spanning tree in distributed system is GHS algorithm. So the algorithm is like, so let's visualize the problem. Let's say we have a graph here. And we want to, so let's say it is a distributed system. Or in this system, we have two nodes that are connected with each other. Also in this system, we have three nodes that are connected with each other. So it is like a graph. So the minimum spanning tree will have n nodes and n minus one edges. So any node can visit to another node, but not necessarily every node is connected with each other. So let's say if we remove this edge, it will be a minimum spanning tree if the edge of it is more than this two edge of it. So in a distributed system, these nodes don't have the information for these nodes. So what will happen is all the nodes will be separated. So this is in the solution. So nodes activate and form initial tiny fragments, and each fragment finds its cheapest outgoing edge in parallel. So both of them will find the cheapest outgoing edge, let's say an edge from here, from there. So the nodes will find the cheapest outgoing edge from here, and these two are connected, and they will choose a leader node, which node, when each node of this system will know who the leader node is. So the information at which edge, let's say X or Y, which would is less, and that one will be, let's say X, the word X is less than Y. So the information will be passed to the leader node, and the leader node also, along with all the nodes in the system, will know that the uh, minimum mode in which you can reach from one system to another is this. So it will establish a connection by this node. And for internal to the system, the same process will work. Let's say it will send uh, signal the outgoing edge. So will broadcast. Also, it will also broadcast in this too. So, and find the cheapest node to connect with each other. And the info, let's say this is the cheapest and efficient, and it will be updated. And also, let's say this is connected with then this node. So then the tree will merge, and it will then the graph will merge, and it will look like this from the first system, and this node from the second system. So this is the minimum spanning tree from a distributed system. And for the follow-up question, real-world event scenario for MSTs are sensor network feature selection in IoT and environmental monitoring. Sensor collect overlapping and correlated data by building a similarity graph for edge words represent feature correlation. The MST identifies the minimal set of sensors needed to capture essential information while eliminating redundancy. This reduces communication cost and power consumption in battery-powered sensor network. So, by building a similarity graph, where edge words represent features co-division, the MSP will identify, uh, so let's say, and what's from this to this and this to this. Let's say these words represent feature correlation, and when finding the MST, the algorithm will identify which feature selection, which feature correlation, sorry, which feature uh, is needed more to eliminate extra users of an IoT device. And also using MST, we can found You can review nature, cluster, and social network by identifying which connections, find minimal set of information nodes or whose activation maximizes information spread, and build user similarity graph where MST identifies correlationship for collaborative filtering. The key advantage is MST provide minimal connectivity while preserving robust structure, making them ideal for scenario requiring efficiency without essential relationships. And for the problem for a tree or graph-based feature index in a memory constrained environment, compare its level allocation and garbage collection as memory management studies. So let's remove all the previous drawings. Sorry. So what is level allocation actually is? The memory is divided in similar size chunks, and each chunk has an address which a program can access and store information. So the access time is of one for allocation and also for deallocation. So it is really efficient and uh, for storing a fixed size information like some node of a tree. Uh, there it can be stored here, and and the memory can be divided initially into parts so it can match the size. So slab allocation is pretty efficient than garbage collection, and the garbage collection automatic memory reclamation by runtime. So it will there will be no fixed size memory, and uh, uh, all the program will use the memory it need, and then the consecutive memory it need. These are not it is not necessary that this will be the same size. So when the garbage collection was it sometimes uh, occurs sometimes we stop the work was occurs during the collection of garbage values from memory. So it is latency quickly decreased, poor and memory fragmentation is moderate. And the allocation throughput is high but impacted by DC cycles because they miss DC cycles and stop the workforce can occur. But there is also a problem in the collection, which is not that much of a problem, but when storing fixed size information, uh, the word information can have various sizes. So let's say this is three, this is three. So internal fragmentation can occur here, but the garbage collection, but compared to the garbage collection, it is really efficient. And the follow-up question is which memory strategy for predictable ML serving? So here you can see that its evolution is superior for online ML system because it has predictable latency of one for accessing allocation and deallocation from pre-allocated pools and no pause times. And T-graph nodes have uniform size, which is ideal for slab allocation and minimal fragmentation due to fixed size chunks. And also no stop the world even of that violate latency budget, so consistent response time under heavy load. Thank you.